we're going to go through some examples where we look at compounds and determine whether they are aromatic, non-aromatic, or anti-aromatic. And you can use the flowchart that I provided to figure this out, but on an exam, you're going to have to be able to do this without having that supplemental resource. So the way I really recommend doing this is just keep in mind the primary criteria for aromaticity. Is it cyclic? Is it completely conjugated? Is it planar? And does it have 4n plus 2 pi electrons? So if we meet all four pieces of criteria, the molecule will be aromatic. If any of these criteria, if any one is not met, then the molecule will just be non-aromatic. And then on the chance that you meet each of the first three criteria, and then number 4, we have 4n pi electrons, that would be anti-aromatic. That's a more rare situation because in most cases we're going to find ways that a molecule can avoid being anti-aromatic, and usually that involves coming out of conjugation or planarity. So let's look at the first example. We have this chain that is completely conjugated. If we draw a p orbital everywhere, you have a pi bond. It's completely conjugated, but the first criteria isn't met. It's not cyclic. As soon as one piece of criteria isn't met, it's immediately non-aromatic. So let's look at the second molecule. Go through our criteria. First, is it cyclic? Yes. Is it completely conjugated? Let's put a p orbital everywhere we have a double bond. Here, 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 and here. The ring is not completely conjugated. Right here is a break in conjugation. So for that reason, it's non-aromatic. In this next example, we have an 8-membered ring, and it is certainly cyclic. Next, let's see if it's completely conjugated. It's p orbital here, 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 and here. So every atom in the ring contains a p orbital. It is completely conjugated. Next question, is it planar? That's not always an easy one to answer. So we're going to come back to that. The final thing to look at are the 4n plus 2 pi electrons. Well, let's count up the pi electrons. Every double bond is 2. So there's 2, 4, 6, and 8. So what we want to do is set our equation 4n plus 2 equal to 8 and solve for n. So we end up with 4n equals 6. N is 6/4. That's not an integer number. So it's definitely not an aromatic compound. Next, we want to decide, could it be anti-aromatic? So what we want to do there is try the same equation with 4n. So do 4n equals 8, n equals 2. That gives us an integer number. Right? But it's still not as easy as just immediately saying it's anti-aromatic. So yes, the 4n rule is met, but we still haven't answered the question of planarity. And there's a general rule of thumb that you can use here. And what that rule of thumb is that in general, if a ring has 7 or more atoms, it has enough flexibility in it that it can bend out of planarity to keep from being anti-aromatic. So I think I mentioned before, a molecule is going to do whatever it can to not be anti-aromatic because that's really, really bad. So in this case, we have 8 atoms. So that is 7 or more. That can bend out of planarity. So we're going to say planarity, no. And if it's not planar, what happens is these p orbitals are no longer going to be parallel. And as soon as you bend those out of being parallel, then that's going to break the conjugation, and it's going to be just non-aromatic. One really important word of caution here, though. Don't take this to mean any ring with 7 or more atoms will not be planar. It only bends out of planarity to stop from being anti-aromatic. If all the criteria is met for something to be aromatic, 7 or more atoms will be perfectly happy to be planar. So there are some exceptions, but in general, if being planar will make it be aromatic, it's going to be, because that's a good thing. So it could be 7, 8, 9, 10 atoms in the ring, totally fine. So let's look at our second example here. So now we have a 7-membered ring. So I'll just write a 7 on the inside here so we don't forget that. Let's go through our criteria. Cyclic. Yes, it is. Is it completely conjugated? Let's go through it. We have a p orbital everywhere you have a double bond. And carbocations reside in p orbitals. So I'm going to make you a note here. Carbocations, but not other cations, reside in p orbitals. So if you see an oxygen cation or a nitrogen cation, that doesn't necessarily mean there's a p orbital there. But a carbocation, yes. So we have a p orbital on every carbon. This is completely conjugated. Next, is it planar? We don't know for sure. So we have 7 atoms, which means it can bend out of the plane, but it doesn't have to. So let's check our final criteria, which is the Huckel's rule. And we'll set 4n plus 2 equals the number of pi electrons. How many pi electrons are there? 2 in this double bond, 2 in this double bond, 2 in this double bond. So there's 6 pi electrons. Solve this for n. N equals 1. It does meet Huckel's rule. So all the criteria for aromaticity is going to be met, except we don't know about the planarity. Well, if everything else is pointing toward the molecule being aromatic, it will go into planarity. It will be planar so that it can be aromatic. So is it planar? Yes. So we're going to say this molecule is aromatic. In our next example, we have a 5-membered ring with a carbocation. So we'll go through our criteria. It is cyclic. Is it completely conjugated? There's a p orbital everywhere we have a double bond, a p orbital where we have the carbocation. It is completely conjugated. Is it planar? We have 5 atoms. That's a small ring with everything completely conjugated. We would expect, yes, that it's planar. And then the final thing is the number of pi electrons. So how many pi electrons do we have? Here's 2. Here's 2. So we'll do 4n plus 2 equals 4. 4n will then equal 2. N ends up equaling 1/2. That doesn't work. So what we want to do next is check for anti-aromaticity. So 4n equals 4, n equals 1. So it actually meets all the criteria in this case to be anti-aromatic. In our next example, we have a similar 5-membered ring, but instead of a positive charge, we have a negative charge. And one thing that you want to recognize is that this negative charge is a carbanion, and that means the carbon has a lone pair on it. So there is a lone pair on that carbon. So let's go through and see if we can figure out whether this is aromatic or not. So the molecule is cyclic. Is it completely conjugated? Well, we know that we have p orbitals where we have the double bonds, but the question becomes, how about the lone pair? Because remember, lone pairs can go in p orbitals or they can stay in hybrid orbitals. So that's going to be something to keep in mind. Is it planar? Most likely it's a small ring, but again, that kind of depends on the hybridization of this carbon. If the lone pair is in an sp3 orbital and this carbon's sp3, then it's not planar. If this lone pair is in a p orbital and this carbon is sp2, then it is planar. So those two are kind of going to go hand in hand. So finally, we need to figure out Huckel's rule. 4n plus 2 equals the number of pi electrons. So in this case, we have 2 pi electrons in this double bond, 2 in this double bond, and if we count the lone pair, 2 there. So let's try it. Let's say that lone pair is in a p orbital, in which case we're going to count it with our pi electron count. So we would have 6. We do that, n equals 1, and it does meet Huckel's rule. So what does this tell us? This tells us that the molecule will be aromatic because that's a good thing, and it can be. So this lone pair will clearly reside in a p orbital, making it completely conjugated. If that's the case, the molecule will be planar and aromatic. So, in terms of what I mentioned here, the lone pair can be in a p orbital or it can be in a hybrid orbital. Well, the easiest way to think about this, it will be in a p orbital if putting it there makes it aromatic. And then if that lone pair is in a p orbital, you count it with the pi electron count.